mathematicians, here are your notes for 3.6, talking about ratios and proportions. So today's goal is to be able to explain the concept of a ratio and use ratio language to describe a ratio relationship between two quantities. That was a lot. Let's dive right into it though. I have two real-life problems right off the bat. So, the vet said that I had to give Maria, my childhood dog, some liquid vitamins. The vet said every day she should get 1 teaspoon for every 20 pounds of her weight. If Maria weighs 15 pounds, how much medicine should she get? Now, without knowing anything about ratios and proportions, I can kind of visualize this one. I can draw a little map over here, and I can say for every 20 pounds, she gets 1 teaspoon of medication. And because 15 is a really nice number, I can break 20 down into smaller portions. We know 5, 10, 15. And based on this picture, if we know that 20 can be broken down into 4 and she only weighs 15 pounds, it makes sense that she would get 3/4 of a teaspoon of medicine. However, if we look at the next problem, Walker is planning a summer vacation. He wants to visit Petrified National Forest and Meteor Crater in Arizona, the 50,000-year-old impact site of a large meteor. On a map with a scale where 2 inches equals 75 miles, the two areas about 1.5 inches apart. What is the distance between Petrified National Forest and Meteor Crater? Now, I could do this one much the same way, but I'm actually going to skip over this problem for right now because I want to show you that even though we could visualize it, there's an easier way to do it using math and the representations it gives us. So let's go into it. What is a ratio to start off? Well, a ratio is just a comparison of two numbers. So you could say the ratio of blondes to brunettes in our class, the ratio of apples to oranges at a store, things like that. On the same hand, what is a proportion? A proportion is a comparison of two ratios. So we've got the basic, and then we've got the little bit more complicated. So an example of a ratio might be there are 5 apples in a store to only 7 oranges. This could be rewritten as 5 to 7, or even as a fraction of 5 divided by 7. A proportion, on the other hand, may look something like this, where we have I would say 5 divided by 7 is equal to x over 14. It's a comparison to say, are these equal, are these unequal? And it usually, in our case, is going to look like a fraction equal a fraction. So what does it mean to have proportionality? Well, essentially that means that they are going to be the same, but look different. So I think this one actually looks a little bit easier with this example. So smaller version of fraction is equal to larger version. So if I wanted this bottom fraction to be proportional or to have proportionality, I would need to make these two fractions equal to each other. Notice our smaller version of our fraction should equal our larger version of our fraction. In order to do that in this case, notice if I want this fraction to have a denominator of 14 and I want to know what's on top, I would have to multiply this entire fraction by 2. So that would make 7 times 2, 14, and it would make 5 times 2, 10. So in order to have proportionality in this set of fractions, my x would have to be 10. Let's look at that a little bit more on the back here. If I give you these two fractions and ask you if those ratios are equal to each other, or are they proportional, what would you tell me? Well, looking at these, it's a little hard to tell right off the bat. We've got a smaller fraction, obviously, and we've got a larger fraction, but how do we know if they're actually equal to each other? Well, that's where this box comes in. We have two methods to determine if two ratios form a proportion or if they're equal. The first method is to simplify the fractions. So in this case, I noticed that they're both divisible by 5. I could do that until they both had the same denominator, whether it be 5, 15, whatever it is, and I would see that these are in fact proportional. However, simplifying can get a little bit complicated sometimes depending on what your denominator is, especially in the case of like 225. That's a really large number that we don't necessarily want to simplify. So the other option we have is to cross multiply. And I'm going to give you a more simple example below. So in other words, are they proportional? In this case, yes. If you want to use these two methods to see if that's true, you absolutely can, but I'm going to show you with some smaller fractions first. So are the following ratios proportional? Prove why or why not. Well, I'm going to show you both methods. The first one is to simplify. I cannot simplify 5/8. It has to stay the way it is. However, I know that if I reduce or simplify this 10 divided by 15, I'm going to get 2 over 3. Upon looking at that, I notice that 5/8 does not equal 2/3, and this is not true. This is not proportional. However, let's use that second method just to prove that this is true. If I cross multiply 5/8 equals 10/15, I should get the same number on top that I do on bottom when I multiply. So 8 times 10 is 80 on top, and 5 times 15 is going to be 75, I believe. Yep. And notice, because those are not the same, that means they are not proportional. If they were proportional, I would get the same number on top and bottom. So in this case, no, these are not proportional. Let's look at the second one and do the same thing. Can I simplify 3/7? No, I can't, but I can simplify 39/91. Off of the top of my head, I don't know what that is simplified, so I'm actually going to go over here to my calculator and see what it says. Oof. It looks like it is actually already reduced, which surprises me because I thought I put one on there that was not, or that was reducible. But since I cannot reduce it, I have to leave it that way. And because as I look at this, I know 7 doesn't necessarily go into 91, I can already tell that this isn't the case. However, if I back it up with my second method, again, I'm going to need to go over to my calculator, but let's cross multiply and see what happens. If I do 3 times 91, oops, that's times 92, my bad. I'm going to get 273 on the bottom. Oh, I should have put that over here. I'm sorry. That's okay. Ignore my oops. And then 7 times 39. I was wrong. My apologies, students. Apparently, one of these can be reduced, and I just did not see the pattern, because when I double check, I do see that it's proportional. And that's a good argument for why we want to check things like that, because as you can see, even I made that mistake. If one of your methods ends up showing you it's proportional, check it with the second method, and then go back and see if you can do anything different. In this case, I don't think I can reduce this off the top of my head, but my second method shows me that it is proportional. So, yes, this one is proportional. That was my own fault for using funky numbers. So, last one here. What actions should we take if we have a missing value in our proportion? How can we guarantee that they're proportional? Well, much like I showed you on the last page, Sometimes it's easy to just see that to go from 7 over to 28 is a times 4. That's a really nice one because if we're multiplying by 4 on the bottom to get to our bigger fraction, we can do the same thing on the top, and it will yield the same result. It's a balance that as long as you're doing it to the top and the bottom, you're good to go. So in this case, 7 times 4 is 28, and 2 times 4 is 8. So r is 8. However, when you have a problem that looks like this, it's a little bit trickier. So I want to show you a second method, and this is the one that I most often use. This one is easy, but this is more common. When you have two fractions equal to each other, what I find is easiest is to cross multiply and set the products equal. Bear with me on that. I'm going to cross multiply here, and I'm going to say 18 times y plus 1. Notice this is a quantity, so we have to keep the quantity together. We cannot break it up. We can't forget our parentheses because it's all together here. It has to be all together there. Keep going and cross multiply the other side. Once we do that, we're going to set it equal. Let's go back to my calculator here, because 9 times 54 isn't one that I have memorized. 486. Now that I have an equation, I can solve this the same way I have been in previous lessons. I'm going to use that distributive property. I'm going to subtract the 18 to the other side. I'm going to be left with 18y equals, per usual, grabbing the calculator, hold on one moment, 468. And then, of course, dividing by 18. And in this case, I'm going to find that y equals 26. And then I can always go back and plug that in. And that's actually what I'm going to do. So if I plug in y equal to 26 here, I'm going to get 9 over 27 is equal to 18 over 54. How can we guarantee that they're proportional? Well, we can check our answer and see. Notice in this case, 27 times 2 is 54. Therefore, 9 times 2 should be 18. Our problem checks out. We did our check, so we know that's the right answer. Again, if you can use this method, great. However, this one is also going to come in handy very often. Let's go back to that word problem before we end. Remember that this said that on a map with a scale where 2 inches equals 75 miles, the two areas about 1.5 inches apart. What is the distance between them? Well, before I didn't have the ability to set up a proportion, but now I do. So if 2 inches is equal to 75 miles here, I know I put a division symbol for equals, but the reason I'm doing this is because I'm associating 2 inches with 75. Those are one comparison of numbers that I am now going to set equal to another comparison. Instead of being a full 2 inches, we're only at 1.5. And I need to know the distance between them. So, if I know that 2 inches equals 75 miles, what does 1.5 inches equal? Now that I have my proportion, same thing. This is, again, why I wanted to show you the last example on the prior page, because going from 2 to 1.5 is not something that we can just easily multiply or divide. So I'm going to use that cross multiplication technique. I'm going to multiply top down to get my first side, my left side. I'm going to set it equal to my bottom up, 75 times 1.5. 0.5. I get 112.5. Notice the other really nice thing about cross multiplying is it removes fractions. So after we've cross multiplied, we should not have any fractions in our equation, because once we have those fractions taken care of, we can just simply solve. X is equal to 56.25 miles. And again, we could check that over here. However, in this case, because it's this weird number, we're going to go ahead and stick with it. So, you have multiple methods to work with ratios and proportions. If you have any questions on your practice or on anything I went over, don't hesitate to let me know.